Okay, this can serve as the review for the first midterm. The midterms are in week 5. We'll do them online between 8 and 8:30 on each of the class days of week 5, Monday, Wednesday and Friday. Typically we'll open at 7:55 if that helps you in any way. I'll send out an email, it might already have been sent out, talking about the exact way that we'll do these things, but Canvas will be open. The exam will be served to you on campus and you'll have to complete the answers on Canvas like you do for the homeworks. If you choose to do them in the privacy of your own apartment, that's fine. You can come to class and do them if you wish. We'll also have Zoom open so people can ask questions ostensibly in the chat on Zoom. I guess we could use a chat on Canvas, but I think Zoom worked well for us last year, and so we'll at least start off doing that for the first time. I encourage you all to look at the practice exam that's been online for a number of weeks now. It shows you exactly how it works. It's about a 15-minute test instead of a 30-minute test, but it mirrors kind of the procedures that we'll use. If you do have a crisis in submitting it, then just take a screenshot of your working or your answers, or send the answers in an email. I guess it's important to kind of timestamp them somehow. Or send them within the next 5 minutes. And so we have maybe out of 100 people, we have perhaps a few people who have to do that each time, and that's not necessarily a problem. But that's the course of last resort if you need to do that. The first test is on the material from the first 3 weeks and also the first day of the 4th week. It's on fluid properties, which is week 1. It's on fluid pressures at a point in week 2. Fluid pressures on surfaces, both planar and curved, in week 3, and accelerating static fluids, the first period of week 4. There are 3 questions, one on each of the days. The day's questions are shown here. The first question includes questions on a question, which includes questions on viscosity and buoyancy. The second one is fluid pressures on structures, and the third one is on linearly accelerating fluids. And so you can check in previous exams to look at the review sessions and tally them up against the material in the tests if you feel that I might be stringing you along in the wrong direction. But pretty much every equation that you need for the test will be talked about today. How to use it, of course, is up to you, but I think this is a complete set of the equations you'll need. For fluid properties, fluid viscosity, we think of a plate with a fluid trapped between it. The plate on the top is moved at some velocity and requires a shear stress or a shear force to move it. And as a result of that, the fluid being anchored on one plate and anchored on the other plate, it moves with the velocity of the upper plate in this case, and it creates a gradient of velocities across it. And that gradient of velocity is used to relate the shear force that's applied to the rate of change of velocity with depth as you go across the plate. And so you can plot these two quantities relative to each other, and the slope of that graph gives you the viscosity. The units of viscosity are Pascal seconds, newtons per meter squared seconds. And this represents the gradient, if you like, of this curve. The question will be on a Newtonian fluid. We don't talk about Bingham fluids in the test, but you know what a Bingham fluid is. We talked about fluid pressures and how they vary in space. The absolute requirement is that this expression is true both for gases and liquids. The difference between gases and liquids are that liquids are much denser than gases and much less compressible than gases. So that when you integrate this equation out for a gas, the compressibility conforms to the ideal gas law, and for a liquid, the compressibility is constant. Because the compressibility of a liquid is constant, then the variation in pressure with depth is linear. But for a gas, because the compressibility varies with the absolute pressure, the pressure versus depth relationship is nonlinear. However, this equation is always true. If it's in a liquid, we can always get the pressure as a function of this equation, which takes the pressure at a given elevation, takes the depth downwards and adds that depth and the unit weight onto it. And we just have to be careful in terms of how you use it. There is no manometry question on the exam, but the components of the manometry rules, I guess, are germane to the understanding. If you go up or down in a fluid, you subtract or add pressures. If you look at the density of a gas, if you go up in a gas, typically because a gas might be a thousandth of the density of a liquid, the density of the gas doesn't matter. And if you use the ideal gas law, you have to use absolute pressures and temperatures, and you have to know the difference between what a gauge pressure is. Gauge pressure is 0 at atmospheric, and so a vacuum is minus 101 kPa, and absolute pressures, absolute vacuum is 0, and it ascends from there. If we look at forces on structures, you know that there are a number of parameters you need to know. You need to be able to resolve the magnitude of the force that acts as a resultant. That resultant force is always equal to the unit weight of the fluid, the depth of the centroid of the plate below the surface, and the area of which it acts. These two components together represent the average pressure. So multiplying the average pressure times the area gives you the resultant force. The resultant force always acts perpendicular to the surface, and it always acts through what we refer to as the center of pressure, which is not the centroid. The centroid is the valence point of the plate, if you like, which you talk about, and you get the expression from that from our diagrams of centroids and second moments of area. So you need to use the depth of the centroid below the surface. So that gives you the force that is acting. But if you want to know the point of action where it acts at the center of pressure, and we define that as a coordinate below the surface in the orientation of the plane, in the slope direction of the plane. And so y sub r is from the surface to the point of action of the force, and it's equal to the slope distance of the centroid, which would be this point here, y sub c, plus some small amount. And you can always get the magnitude or the location of where the pressure acts, the center of pressure, as equal to yr. And it's always equal to the slope depth of the centroid, which is this magnitude here, plus some small amount. And as you get deeper and deeper below the surface, this amount will reduce, but this amount is always given by the second moment of area about the centroid, the slope distance of the centroid of the plate, and the area of the plate. This you can always get from standard results, and we've looked at them in class. And if you think you have a question like this on the test, then you might have those available ready for you to use. I won't supply them in the test. If you're looking at structures, we have these two things defined. We have the magnitude of the force defined, and we have the location where it acts at y sub r. We can take moments about any point. And so if you, for instance, know where the force acts relative to that moment, relative to that pivot, for instance, and you know what the magnitude of the force is, you can always write the moment as being equal to this lever arm multiplied by the resultant. And so you can always do that. You can choose any point you wish to do this, and this should be true. But if you're looking at a structure where you have a specific pivot point, then you should definitely use that pivot point to do a calculation for moments, because you're typically balancing moments. We've gone through examples in the class for gates that open on pivots. In the same way that I said above, if you know the forces that are acting, you can divide the trapezoid that represents that distribution of pressures into a rectangular one, I guess, which is this, and a triangular one, which is this. And you can take moments about a point by taking the resultant force for the rectangular distribution, which has to be at half height. This would be the location for a gas, which would be basically constant pressure as you go with depth, and multiply it by some lever arm of the point you're taking it about. And you can take the point of action of the resultant of the triangular distribution And we know the triangular distribution will act at a depth, whoops, this height here will be 2/3 of the height of this triangular wedge. And so that's the standard result. So if you have an intersection of a plate with a surface, you can just use this triangular distribution, and you know that the resultant will act 2/3 down from the surface. If the surface is not intersecting the top of this plate, say this gate here, then you have to use this full distribution. And if you use this full distribution, if you did this calculation here by adding both, the resultant for these two forces would be the sum of these two, the square one, or the rectangular one and the triangular one. And then the unknown value would be the location where the combined forces F square and F triangle would act, and that would be the absolute location of it. So you can do that, or you can absolutely use this parallel axes theory to tell you exactly what y sub r is relative to the surface. So look through your notes to figure that out if that's not clear. For buoyancy, buoyancy merely notes the fact that if you take a volume and you remove the fluid from that volume, the weight that was originally acting in this is no longer acting, and therefore there's an imbalance because the pressure acting at depth is now much larger than the pressure acting at a shallow level. And that difference in pressure is given by the weight of the fluid that you've removed. So Archimedes' principle absolutely says that the buoyant force is equal to the unit weight of the fluid that's displaced by the volume multiplied by this volume. If the structure that has the fluid removed from it has some weight, and if that weight also includes the air which has replaced it, you might include that in that weight also, then resolving these for the net buoyant force would be the sum of these two values. If it's air and the unit weight of air is negligible, then this might be 0 if this is a weightless container. But otherwise you have to balance the forces to be able to do a free body diagram vertically. And the final topic, I guess, is accelerating fluids. Linearly accelerating fluids, not rotational accelerations. And I suppose there are two things to realize. One, if you do this in a closed volume, then the fluid can't reorganize itself, and so it can't set up a free surface. And so if you look at the pressure distribution as you go from the rear of this closed volume to the front, the pressure will actually change according to this expression here. And that is that the pressure change is going to be given by the unit weight of the fluid, gravitational acceleration, and any acceleration in the vertical z direction if it's going upwards. And so this just means that the pressure distribution with depth will be, it'll gain pressure faster as you go down. And if you're accelerating it horizontally at some acceleration ay, not a velocity, constant velocity won't do anything to the pressures, but a constant acceleration will change them, then you get a pressure distribution across the structure, which is given by this gradient, which is proportional to this acceleration in the horizontal direction, the y direction in this case. And so these two expressions define this response. But this response is for a closed container, so that's important. If you cut the top off this and allow the water to reorganize itself, then it will get a free surface. And we know that from these expressions, we can manipulate them in a certain way to say that the gradient of that surface, dz dy, which is just this slope of this curve, is given by the acceleration that you apply in the y direction, gravity, which is always acting, and any acceleration that you might apply in the z direction. Z is always positive upwards in our coordinate system, so you need to retain that. And if you know, for instance, what the slope of this surface is, you can calculate either the accelerations, or if you're defined an acceleration, you can calculate what this slope would be. And it matters that you keep the sign convention that we've used, which in this case would be, well, I guess in this case it's in the y direction and the z direction. So a rocket accelerating upwards would be a positive acceleration. Gravity accelerating downwards acts downwards, but this is always a positive quantity in this equation here. And that's about it. So those are the topics of the class, of the midterm rather. Okay, good luck. Thanks.